In this video, we will work through an MCAT-style passage focused on radioactive decay and its different types. I will read the passage and the accompanying questions. If you prefer to read the passage on your own, feel free to pause the video, read through the passage carefully, create a passage map, and attempt each question before reviewing the solution. Without further ado, let's get started. Good luck. Proper immobilization and storage of radioactive waste is of critical importance. To better understand the chemical and the physical interactions that occur between radionuclides and solid matrices suitable to their stabilization, scientists conduct sorption studies. Figure 1 illustrates a sorption isotherm, which describes the relationship between the concentration of radionuclides adsorbed on the solid matrix and the concentration remaining in the liquid phase. Here's figure 1. Figure 1 says the general sorption isotherm. At the low radionuclide concentrations, the isotherm shows a linear region known as the KD region, where the interaction between the solid and the liquid phases is reversible. This relationship can be expressed as the following equation: C solid is equal to Kd times C liquid. C solid is the concentration of the radionuclide adsorbed on the solid phase. It's measured in kilograms per kilogram or mole per kilogram. C liquid is the concentration of the radionuclide in the liquid phase at equilibrium, and it is measured in kilograms per liter or mole per liter. Kd is the distribution coefficient representing the ratio of the radionuclide's concentration in the solid to that in the liquid. As the concentration of radionuclides increases, sorption becomes nonlinear, corresponding to the Freundlich region. The Freundlich equation for this region is C solid is equal to Kf times C liquid to a power of n. Kf is the Freundlich constant, n is the intensity factor, which is a measure of sorption nonlinearity. The primary solid matrix used for radionuclide immobilization is cement. The alkaline pore water in cement exhibits elevated hydroxide ion concentrations, which promote the sorption and precipitation of cationic radionuclides in the form of hydroxides, oxyhydroxides, or oxides. This process significantly reduces radionuclide mobility, enhancing the safety and long term stability of radioactive waste storage. Question number 1. Uranium undergoes many radioactive decay processes until it reaches its more stable form, Pb206 or lead 206. Uranium is often found in its oxidized form, UO to the superscript of 2 plus and a subscript of 2, which can precipitate as insoluble uranium hydroxides or oxides. Which of the following best explains why, even though uranium undergoes radioactive decay, it is found in its cationic form, with the loss of 2 electrons under the alkaline pore water conditions? Option A says the alpha decay of uranium releases a helium atom and it removes electrons from the outermost shell. Option B says uranium undergoes nuclear decay but acts like a transition metal and is found in its cationic form. Option C, uranium 238 undergoes beta minus decay to lose electrons and form the cationic form of uranium. Option D says radioactive decay removes electrons and leaves uranium in its cationic form. Question number 2. Which factor increases the binding of radionuclides on the sorption matrix at low radionuclide concentrations? Option A says a decrease in Kd. Option B says a decrease in the slope of the linear region. Option C says an increase in the value of N, and option D says an increase in the value of Kd. Which element is formed when the radionuclide francium 223 undergoes alpha decay? And the options are listed. Question number 4. Scientists set up an experiment to measure the voltage drop of an electrochemical cell over time. They placed francium 223 at the anode and copper at the cathode. The standard reduction potential for francium is approximately minus 2.90 volts, and for copper, it is positive 0.34 volts. Francium 223 is an unstable nuclide that readily undergoes alpha decay. Its half-life is about 22 minutes. The electrochemical cell was operating properly and all components were functional at the start. What happens to the voltage drop across the cell after a few hours? Option A, the voltage across the electrodes remain at positive 3.24 volts. Option B, the standard cell potential or voltage is unaffected. Option C, the voltage drop increases over time. Or option D, the voltage drop decreases over time. Now we're going to analyze the passage paragraph by paragraph. We will identify important information and determine the main idea of the passage. The first paragraph explains why scientists use sorption studies, which gives the purpose behind performing sorption research. The second paragraph introduces Figure 1 to explain its purpose. It shows how the radionuclide concentration in the solid matrix relates to its concentration in the liquid phase. The focus is on clarifying the relationship between the two variables presented in the figure. The third paragraph elaborates more on Figure 1 by describing the linear reversible region of the isotherm known as the Kd region. It defines Kd and quantifies the relationship between the solid and liquid phases using the equation provided. Paragraph 4 defines each variable in the Kd equation, clarifying the physical meaning of the solid and the liquid phase concentrations and the significance of the Kd as a distribution coefficient. This paragraph expands on Figure 1 by introducing the Freundlich region. It presents the Freundlich equation to describe and define its key parameters. This paragraph builds conceptually on the previous one, and it shifts from the linear Kd behavior to the nonlinear Freundlich behavior. The last paragraph introduces a shift in concept. It moves from explaining the figure to describing how radionuclides transition from the liquid to the solid phase. It explains the chemical mechanism behind effective radionuclide immobilization and long-term radioactive waste storage. The main idea of the passage is the following. Scientists use sorption studies to better understand the chemical mechanisms behind the effective immobilization of radionuclides by analyzing key aspects of sorption isotherms. Let's move on to question number 1. After working through this passage and also its questions, which answer choice do you think is the right answer to question number 1? If you picked answer choice B, you are correct. Question number 1 reads, uranium undergoes many radioactive decay processes until it reaches its more stable form. Uranium is often found in its oxidized form, which can precipitate as insoluble uranium hydroxide or oxides. Which of the following best explains why, even though uranium undergoes radioactive decay, it is found in its cationic form with the loss of two electrons under alkaline, poor water conditions? So, it is true that uranium undergoes radioactive decay and is often found as a cation. However, these are two separate aspects. The radioactivity of uranium involves changes in the nucleus, while its cationic nature depends on the behavior of the valence or outer shell electrons. When uranium undergoes radioactive decay, its nucleus is transformed to increase its nuclear stability. In contrast, uranium forms a cation because it can lose its valence electrons, which are located on the outside of the nucleus. Therefore, option B is correct. Uranium's tendency to exist as a cation reflects its ability to act like a transition metal. Option A is not correct because alpha decay involves the release of a helium 4 nucleus from the atom's nucleus and it does not remove any electrons. Option C is not correct because beta minus decay emits an electron or a beta minus particle from the nucleus and it does not affect the valence electron. And option D is not correct for the same reason. Radioactive decay involves changes in the nucleus and it does not directly remove valence electrons. This question does more than just test your general understanding of radioactive decay. It goes a step further by assessing your grasp of what is happening at the atomic level. It evaluates your understanding of atomic behavior. Sometimes the MCAT provides detailed information about small concepts, but then asks a question that requires you to step back and apply a broader understanding. In this case, you are not expected to have specific knowledge about uranium's behavior. Instead, you are expected to reason your way to the correct answer. As you saw, options A, C, and D all focus on similar ideas. Answer choices A and C incorrectly combine specific types of radioactive decay with the loss of outer shell electrons. Answer choice D is also incorrect because it suggests that all forms of radioactive decay involve changes in valence or outer shell electron, which is not true. The key takeaway here is that you already have the background knowledge needed to answer questions like this correctly. What the MCAT truly tests is your ability to think critically, analyze new scenarios, and apply what you know to unfamiliar situations. So always remind yourself you already possess the knowledge you need to succeed. With that mindset, let's move on to question number 2. Question number 2 reads: which factor increases the binding of radionuclides on the sorption matrix at low radionuclide concentrations? If you pick D, you are correct. At the low radionuclide concentration, the sorption isotherm graph follows a linear process, which is known as the KD region. In the KD region, the relationship between the concentration of radionuclides adsorbed on the solid matrix, which is depicted as C solid, and the concentration remaining in the liquid phase or C liquid is given by the following equation provided in the passage. C solid is equal to Kd times C liquid. If you rearrange this equation, you will get Kd is equal to C solid divided by C liquid. Here, the Kd, or the distribution coefficient, represents the sorption ability of radionuclides for the solid matrix. A higher KD means that for a given liquid concentration, more radionuclides are adsorbed on the solid, or that the value of C solid is increased. This directly translates to a stronger binding or greater immobilization of the radionuclides. Therefore, an increase in KD increases the binding of radionuclides on the sorption matrix at low concentration. And option A is wrong because a decrease in KD results in a lower C solid, or that a decrease in concentration of the solid radionuclides, which translates into a weaker binding. Option B is wrong because of the same reason as A. A decrease in the slope corresponds to a decrease in KD, and a decrease in KD results in a decrease in the variable C solid, which also means a weaker binding. Option D is not correct because an increase in N applies to the nonlinear or the Freundlich region. The question stem is asking about the KD or the linear region, which refers to the low concentration region. So the correct answer choice is D. This question is really testing whether you understand the graph and the equations presented in the passage, and not whether you memorize random facts. The passage tells you that the KD region represents the linear portion of the sorption isotherm, and it even gives you an equation describing that relationship. If you take a moment to rearrange the equation, the connection between KD, C solid, and C liquid become much clearer. This step helps you see how changes in KD affect the amount of radionuclide that bind to the solid matrix. Now, looking at answer choice A and B, they basically mean the same thing. A decrease in KD is the same as a decrease in the slope of the linear region. Both would mean less binding, so they are both not correct. Option C talks about the Freundlich region, which only applies to a higher radionuclide concentration, not at the low concentration mentioned in the question stem. So the key takeaway here is this. When you see a question like this on the MCAT, go back to the main idea of the passage and connect it to the data or the equations presented. You do not need to memorize formulas, you just need to interpret relationships logically. Let's move on to question number 3. So, question number 3 reads: which element is formed when the radionuclide francium 223 undergoes alpha decay? If you picked option B, you are correct. When francium 223 undergoes alpha decay, it emits an alpha particle, which is a helium 4 nucleus. An alpha particle has 2 protons and 2 neutrons. When radioactive decay happens, the mass number changes from 223 to 219 because it loses 4 nucleons, which are 2 protons and 2 neutrons. The atomic number decreases by 2 and it goes from 87 to 85 because it loses 2 protons. The element with an atomic number of 85 is astatine or AT. So option B is correct. This question is a straightforward one that tests your basic understanding of alpha decay. If you know what alpha decay is and apply some simple math, you can easily answer this type of question correctly every time. Here's question number 4. It says scientists set up an experiment to measure the voltage drop of an electrochemical cell over time. They placed francium 223 at the anode and copper at the cathode. The standard reduction potential for francium is approximately minus 2.90 volts, and for copper, it is positive 0.34 volts. Francium 223 is an unstable nuclide that readily undergoes alpha decay. Its half life is about 22 minutes. The electrochemical cell was operating properly and all components were functional at the start. What happens to the voltage drop across the cell after a few hours? So the question does tell you that francium 223 is radioactive with a half-life of 22 minutes, which is a very short half-life. After a few hours, essentially all francium 223 will have decayed to its daughter nuclei. Francium 223 will no longer be present at the anode after just a few hours. The decay changes the chemical identity and the availability of the anode material, so the original anode reaction can no longer occur at the same rate. Furthermore, as the active anode material is consumed, the cell cannot sustain the original redox reaction and the measured cell voltage will fall eventually to zero if no other anode material replaces the original one. So the correct answer to this question is D. Option D is correct. So this question was a bit advanced. This question tests your conceptual reasoning and your ability to integrate topics. In this case, radioactive decay and electrochemistry. The first thing you should do when you encounter a question like this on the MCAT is to read the question stem very carefully. And then you have to ask yourself, what is the question really asking? This question gives you numerical values, and your instinct might be to jump into calculations to find the cell potential. However, if you identify the purpose of the question, first you will often see that many of those calculations are not necessary. When you avoid such unnecessary calculations, it will save you a lot of time on the actual MCAT exam. So, first, determine what the question wants. Next, recall the relevant information and the relationship between radioactive decay and electrochemistry. Finally, predict how the decay will affect the electrochemical cell's function. The key here is to focus on what the question is asking, then apply your conceptual knowledge to solve it. So for question number 4, the correct answer was D. I hope you found this practice and the explanations helpful. Be sure to check out the other videos in this playlist for additional review and practice. Thank you very much for watching and happy studying. Good luck on your MCAT journey.